Welcome back, everybody, to INE's CCA Data Center Nexus switching class. Today we're going to continue our discussion of the virtual port channels that we started yesterday. We're also going to be talking about Fabric Path, which is an alternative basically a layer 2 routing protocol that we can use in the inside the data center. Now, before we get started with the additional topics and continue with VPC, if anyone has any questions about what we talked about yesterday, feel free to type those in now. A couple questions I had here to start. One was if I had about the peer keep alive on the Nexus 5000s. So as I was mentioning, Nexus 5K is mainly a layer 2 only switching platform. It does have the layer 3 add-in card that you can add on. Some of the platforms, not all of them, take it, but that would allow you to do like OSPF routing or EIGRP routing. Basically make it like your layer 3 default gateway of your end hosts. But normally, by default, that's going to be mainly a layer 2 only platform. So the question then becomes, if we're doing VPC, the virtual port channels, and we need that layer 3 keep alive link, the VPC keep alive link, the peer keep alive, then how do we do that if it's a layer 2 only platform? So you'll see that there are actually some basic layer 3 functionalities built in, even if you don't have the add-in card. So you can configure interface VLANs, you can put IP addresses on those, and then you can at least send basic pings back and forth between the devices. So if you don't want to use the management 0 interface, you could take in-band data links, like two physical 10 gig E's. You could channel those together, put them in an access VLAN, and then use the switch virtual interface, the layer 3 interface, in order to be the source and destination of the keep alive. Now, really, the design advantage of doing that is that potentially, if your management link goes down, then the pure keep alive is still there. But again, when we're looking at the design difference between the 5K and the 7K, 5K really isn't a redundant platform to begin with because there's no additional supervisors, there's no additional line cards. It's basically just the fixed switch, either the 1U or the 2U, depending on the platform that they're talking about. So you could use the SVIs. That would be another configuration option there. There's another question. Would the commit rollback help when the VPC configuration was messed up in a VPC change? You can. There are some ways to do the configuration management with checkpointing. It's not as intuitive as it is in like iOS XR, where every time you make a change, you're making a commit, and then you can clearly roll back and forth between the versions. I'm not going to show that now, but after class, some of the additional videos that we go over, just some more of the management techniques in detail of NXOS, I will be talking about that. So when we go over examples of setting up SNMP and then actually looking at how do you send traffic to the collection station, setting up NetFlow, actually sending it to a NetFlow collector. So there will be some more targeted videos on those particular topics. If you want to see exactly how it's working from like a real design point of view. Now, one of the issues that I ran into towards the end of class yesterday was with the Nexus 5000. We were looking at the active-active fabric extender, or the FEX topology, where basically we had the two parent switches, the Nexus 5Ks, then they were going down both dual-homed to the fabric extenders in a VPC environment. And one of the configurations I was showing is the switch profiles, or the config sync, that would be used to make sure that the configuration stays the same between the parent switches. Now, the first portion of the configuration I was doing, the initial commit worked. The second commit it had an error message, said that the verification was failing. And one thing I forgot to mention about that, and I want to bring up the documentation here, is mainly if you are using config sync, you basically have to use it exclusively. So you pretty much use config sync for 100% of your configs, or you're not going to be able to use it at all. So from the main documentation page, if we go to products, then to switches, then to data center switches, then to the Nexus 5K, the configuration guides, then this is going to be under configuration fundamentals, or system management here. Okay, system management, and then switch profiles. So like I mentioned earlier, you do definitely want to spend some time reading through the documentation, because there's a lot of specific caveats for the individual versions and then the different hardware platforms that we're working with here. But one of the issues here, if we look at the configuration validation, there's a check that's run that's known as the mutual exclusion check, or the mutex. It says, as part of the commit process, the mutex occurs on both switches, so your local peer and the remote peer, basically to make sure that when you apply the config, it's actually going to work. Okay, but this subnote here is what the problem that I specifically ran into. It says, prior to release 5.13, and we're actually running 5.13, so this applies to the version that I was demoing. It says, an interface config could be partially present in a switch profile and partially present in the running config, as long as there were no conflicts. So that was in the older versions. Starting in release 5.13, port channel interfaces must be configured fully either in the switch profile mode or global config mode. So basically what this means is that since I had configuration going on before on the 5K, and we were doing the port channel config, we were doing the VPC config, then we had some access VLAN configurations on the switch ports. When I went to apply the config sync, it basically said, well, you can't do the port channeling config in the switch profile because you already had it outside in regular global config. So you would basically have two options. What you can do is, well, you could just not run config sync at all and then just manually make the changes. But what you can do, if you do want to use this feature and you didn't use it from the get-go, there's an option that allows you to import your previous configs. So you say import the running config under the switch profile, and it basically then makes those commands be under the control of the config sync process as opposed to the normal global config. So had we done it using config sync from the initialization, so we boot up the switch, give it a management address, give it host name, configure Cisco Fabric services over IP, configure the switch profile. Then from that point forward, you can use config sync. But if you didn't do it in the correct order to begin with, then you're going to run into those failures. So I'm not going to go back and go through the config again. You definitely will want to try this out within the scope of your CCI preparation before you actually get to the lab. But basically, if we were to delete all the configs and then start it again in the same order, then it would be fine. Okay, but again, a lot of these features in NXOS are very highly subject to their order of operations, where you have two identical configurations, one works, one doesn't work, simply based on the order that the commands were entered in. And really the only way to figure that out is either to try it on the command line or to read through the documentation and see the particular release notes for that individual version. Okay, so let's spend a couple minutes recapping real quick what we talked about yesterday, some of the different VPC topologies. The first one we started with here was the two Nexus 5000s, and then we had the downstream neighbor, which in this case was a router, router 1. And the key portions that are making up this topology again, the first thing that we have is the peer keep alive link. Okay, the peer keep alive link in this particular case was running on the management 0 interfaces of the 5Ks. We also saw some examples on the Nexus 7K that we were running that in band on the data plane. So here these were the management 0 links. That's going to allow us to establish basic IP reachability between the neighbors. Once we have that up, then we have the peer link. Okay, the peer link again was what we use with the Cisco Fabric services over Ethernet, or the CFSoE, in order to actually synchronize the control plane between the devices. So not only the control plane in terms of like the MAC address forwarding table, the ARP cache, the IGMP snooping database in the case that we're running layer 2 multicast, but also that's going to be used to exchange the consistency parameters, which is going to be things like the speed, the duplex, the MTU, any of the particular options of the VPC members. We need to make sure that those are synchronized between the VPC peers, otherwise the member interface is going to fail when we actually try to allocate it. Okay, so once we have the keep alive done, once we have the peer link done, then the next step is to actually configure the VPC member ports. So in this case, this was the two Ethernet 1/24s. We put these in an interface port channel, like interface port channel 1, whatever local significant number. We say that this is a VPC, so we'll say VPC 1, and then whatever our layer 2 config is, like switch port, mode, trunk. Normally we would want to say like this is the spanning tree port type network, depending on what type of downstream device we're going to. In this case, if we're going to an end host, we would probably say the spanning tree port type is edge, so we wouldn't be running the normal BPDU exchange. That link would not be part of the synchronization process of rapid spanning tree protocol. But again, it's mainly these three main components, what we need to deal with: the keep alive, the peer link, and then the actual member ports. Okay, the second example we had then was doing this from the 7Ks down to the 5Ks. As we saw, these two 7000s, they were VDCs that were part of the same physical chassis. So the additional caveat of this config is that on the management 0 ports, they're not able to talk to each other because it's the same physical link that's actually used on the supervisor. So if these were two separate physical chassis, we could run the peer keep alive link over management, but in this case, since they're VDCs in the same chassis, that's not going to work. So what we did then instead was to take some of the M ports, so these are the layer 3 M1 module ports, we put those into a port channel, then on the port channel, whatever interface, port channel 1, 2, 3, we said this was not a switch port, so that was making it a native layer 3 routed interface. And when we do this, the other design consideration is to make sure that it's in a VRF. So we said it was a VRF, the member VRF, whatever the name was. I said it was peer, keep alive. This is just to make sure that it's isolated from the rest of the data plane traffic. So if you have some sort of actual looping in the network because there's maybe a cabling problem or some control plane issue, then the peer keep alive link should not be affected by that, because if it's in a different virtual routing and forwarding instance, a different VRF, then traffic cannot move from the global routing table or the default VRF into the user-defined VRF, which I called peer keep alive in this case. Okay, then likewise, once the peer keep alive was up, we have the peer link. Okay, the peer link, we want to make sure that this is at a minimum 2 10 gig E links that are in a layer 2 trunked port channel. So it's a 20 gig port channel. Once the Cisco Fabric Services over Ethernet has synchronized between the two of them, we would see one of them is elected the primary role, one of them is elected the secondary role for the VPC peers, and then we can go on to our final step, which is to create the VPC. So in this particular design, we had two separate VPCs. We have VPC 51 or whatever the number was that was going down to the first 5K, which exists on this link and this link. Then the second VPC, 52, that's going down to the second 5K on this link and this link. So this is a real important point. We need to make sure that we're actually assigning the VPC member ports to the correct physical links. One of the potential common config errors here would be to say that both of these are 52 or that both of these ports are 51, when in that case that's not going to work. It has to be going down to the same downstream switch. Now we're also going to see another more enhanced example of this today in a design that we call back-to-back VPCs, where the 7Ks are doing a VPC downstream towards the 5Ks. The 5Ks are also doing a VPC upstream towards the 7Ks, and we have 4 physical switches, or in this case 3 physical switches because 2 of them are made up of the VDCs, but normally 4 physical switches that logically look like 2 switches. So a pair of them upstream, a pair of them downstream. The pair upstream looks like one bridge, the pair downstream looks like one bridge. And then we run in, we have that case where we have the 16 or the 32-way 10 gig port channel. So 160 gig or 320 gig, depending on the particular models and line cards that we're actually using for the member ports. Okay, the next variation we had then was going down to the fabric extenders. Okay, this is where we have the active forwarding for the FEXs. So the first Nexus 2000 was paired with the 5K1 and the 5K2. So this means that there's going to be a VPC here and here, and a second VPC here and here. Now again, the potential problem we run into with this is that now we have 2 separate control and management planes which are existing on the 5Ks upstream, and they're managing the same downstream fabric extender. So this means that if you configure an access VLAN on one of the parent switches and you don't configure it on the other parent switch, then you're going to have some problems with your actual data plane forwarding on any of your hosts, like your physical servers that are actually attached to the FEXs. So that would be one of the reasons why you may want to use the config sync process between the 5Ks, because we're referencing the same, basically, fabric extender host ports that are going down to the actual end devices. But then again, as we saw, the caveat you run into, either you have to basically use config sync for 100% of your configuration, otherwise it's going to disallow you to do commands in global config and the config sync mode at the same time that overlap. So you basically either don't use it or use it for 100% of the config. Okay, the next variation then was similar to this topology with one minor change, that we have an end host that is now dual homed to the fabric extenders. So in this case, there's actually multiple levels of VPCs here. So we have a VPC that's going from 5K1 to 2K1, from 5K2 to 2K1, a second VPC that's going from 5K1 to 2K2, and the second VPC that's going from 2K2 down to, or 5K2 down to 2K2. Okay, then there's actually a third VPC that is configured on the fabric extenders themselves that go down to the end host. Okay, this is what is known as the enhanced VPC. So it means that we're doing active-active from the actual end host up to the fabric extenders, and we're doing active-active from the fabric extenders up to the parent switches. Now, this particular topology is not supported in all cases. It's not supported on the Nexus 7K when you're using the FEXs as attachments to the M1 line cards. It's also not supported on the older versions of the Nexus 5K. So pretty much only the newest versions are going to support that. But configuration-wise, it's just a normal VPC config between the two 5Ks. We configure the port channels and then say that those are the switchport mode FEX fabric. Those are the FEX associates, so those are the downstream links towards the fabric extenders. Then on the host ports from the FEXs down to the actual final destinations, we just simply configure that as a port channel on both sides. We don't need the VPC keyword, which is a key point here, but it actually ends up to be a VPC. So you have active-active from the host to the fabric extender, and then again, active-active from the fabric extenders upstream to the 5Ks. Okay, there's a question here. If we use config sync under profile 1 and add some configuration, would we need to enter config sync instead of config T? Yes. So in general, if you are going to use config sync, you need to do it for pretty much everything. Otherwise, if you end up in those inconsistencies where some commands were entered in regular global config, some commands were entered in config sync, the next time you go to config sync and try to commit a change, it's going to give you that failure message because of that mutual exclusion check, that mutex check. And if we looked at the, and you can see the syntax here, let's go back to the documentation. There is a show command that will tell you what is the failure. So if you look at the show switch profile, the name, and then the status while you're in config sync, it'll tell you if there's an error because of the mutex check, the mutual exclusion. So in general, unless you've already used config sync for everything, you're not really going to be able to use it. It's more like from your initial implementation, you start using it, and then you're going to stick with it. Okay, another potential design issue you need to think about with this is that if you're using config sync, you need to make sure that even the port numbers are the same between the switches. So here we have the 5Ks going down to the FEXs. I need to make sure that the ports here, which are E1, 4, and 5, are the same numbers, E1, 4, and 5, that are on the other parent switch down to the FEX. Otherwise, if I try to apply a config change on either of these basically member ports of the VPC, then it's not going to apply to the correct interfaces on the remote peer of the config sync. So there's some additional design considerations you need to take into account with that. Okay, there's another question here. In the eVPC, the VPC number and the FEX number on both the primary and secondary must be the same, correct? So if you're doing active-active from the parent switches down to the FEXs, pretty much 99% of the config needs to be equal between them. Really, the only thing that would be different between the 5Ks would be like their host names, their management IP addresses, and then you could have maybe like different security policies on them, but generally you would want that type of stuff to be the same. So anything that's really related to the data plane config, like your VLANs, your VPCs, your trunking config, all of that is going to have to be pretty much 100% equal between the two of them if you want to use active-active, or if you're using config sync along with active-active. There's a question, so the problem of interface numbers can occur only when you are dual homed. Well, the problem with the interface numbers really only occurs if you're doing config sync. So you don't necessarily have to match the numbers if you're doing the configuration manually. We could plug or we could wire the switches however we want. It's usually for clarity that you do use the same numbers, so it makes the management of the config a little bit easier, but it's not really a strict requirement. Okay, it only becomes an issue when you use config sync, because if I have a config applied to E11 and I push it over to the other switch and their E11 is not actually wired to the same destination, then there's going to be a problem with the end result of it. There's another question here. There's an option to import specific interface config only to the config sync. That's right. So you can say when you're importing the config, and let's just search here for import. Importing configuration, importing a switch profile. You can say, I want to add just that particular link to the profile. So this is going to say, take the commands that were under Ethernet 1/2 and now make those to be managed as part of the switch profile. You could also say, basically, to import everything, or to import everything with the exception of a particular link. So the idea for this is that you started your configuration not using config sync. You want to use it later, so then you have to import what was in global config to the switch profile so that you don't run into that mutual exclusion check error. There's a question or a comment here. Show run switch profile is a helpful command to see what has been configured with the config sync. That's right. So in global config, you'll see under the switch profile exactly what has been changed under the profile. So basically what config sync owns versus what your global config owns. So after class, once we go through some additional videos on more specific configuration examples of these, I will have some more detailed examples on the config sync process. But usually, as long as you do it in the correct order of operations, you normally don't run into these problems. You just need to make sure that basically everything is 100% the same between the two platforms. Okay, there's a question on orphan ports. Does this imply that when two switches are VPC peers that every end device must be VPC attached to? Yes, it does. And we're going to explore this in more detail today as well. So the question is saying, if I were to have two VPC peers, so let's say we have a 7K1 and a 7K2. Okay, between these two switches, we have the peer link. So the peer link, that's our control plane synchronization between the two different control planes, two different management planes, and then we also have the peer keep alive link. A peer keep alive link again is going to be used for just the UDP ping back and forth between them. Normally, what we would have then from the VPC peers is their downstream facing links are going to the same devices, so everybody is basically dual attached. So if we have a switch downstream, let's say that this is like an access switch, a 2960. Okay, we're going downstream towards them. This is going to be one of the members of the VPC, so we'll say this is VPC1. This is another member of the VPC, VPC1. So this downstream switch, this is not considered an orphan because it's dual attached to the VPC domain. This is ideally what we want. Okay, what would be considered an orphan is if we had another switch over here, let's say another 2960, that's going only to one of the VPC peers. Now, the reason that you do not want to do this, first off, is that if I have a host that is coming in on, let's say, Nexus 7K2, so traffic is coming in here, the only way to get to this orphan switch is then going to be to go across the peer link. And the peer link's aggregate bandwidth is generally going to be much lower than the aggregate of all of the VPC members and then possibly of the orphan ports. So we ideally don't want to use the peer link in the data plane. We want it mainly just for control plane synchronization. Okay, this is one reason you don't want to use the orphan ports. There's also a case we'll see today when we get into different failure scenarios that if one of the switches goes down, okay, well obviously if 7K1 goes down here, the orphan port is going to be isolated because that's its only physical connectivity. But let's assume here that the first switch goes down, so it crashes completely. The primary role of the VPC is then sent over to the secondary switch. So originally this was secondary. This switch now becomes what's known as operational primary. So it's configured as the secondary based on its priority, but it's actually running as the primary. Okay, then at a later time, the primary comes back. Okay, so this guy's okay now. The issue becomes that there's certain cases where this orphan port is not going to be able to send packets into the data plane, regardless, even if the upstream VPC peer is working. And they're kind of odd cases. We will take a look at them today, but to just avoid this issue completely, if your switches are VPC peers, you generally should not be using them for orphan port connectivity. You should be only using them for VPC member connectivity. For any other devices that are only single attached, you should move them to other switches that are not the VPC peers. So a regular switch like your Catalyst 6500 that's running normal rapid spanning tree or multiple spanning tree, that's not going to have issues with the orphan ports because we're using the normal spanning tree forwarding rules. But in the case of VPCs, we're using that modified VPC check rule that says if a packet comes in the peer link, I can't send it out the member ports of the same VPC member that the other remote peer has. But if it comes in the peer link, I can send it to my orphan ports. So the forwarding rules change and they get a little bit more complicated. So really just to avoid this in the design to begin with, you just don't use orphan ports on the VPC peers at all. There's a question, it is only an orphan port if the VLANs are the same as the VPC domain. Correct. So if you're doing like layer 3 routing, or if it's a different set of VLANs that are not part of the members, then it's not considered an orphan. So if we were to say on this 2960 that is not an orphan, let's say that it's using VLAN 10 down here and VLAN 20, but the other switch that's single attached, if this is using VLAN 30, for this particular VLAN it doesn't count as an orphan because those the VPC forwarding rules are only applying to the specific VLANs that are part of the VPC members. Okay, but the issue then becomes, further than this, on your peer link, you would want to remove in the trunking allowed list any VLAN that is not part of the VPC member ports. So in a normal design, you would not be allowing VLAN 30 to go across the peer link, which means that if this is the only layer 2 interconnect between the VPC peers, VLAN 30 is going to be isolated to begin with. Okay, so you could add another layer 2 trunk link that's running normal spanning tree and then use that to forward the VLAN 30 traffic, and then it's going to behave as if it was just a normal switch, like how 6500 would behave. Okay, there's a question. I think if you have an issue with either the keep alive or the peer link, anything connected just to switch 2 will not be able to communicate if the device is in the VLAN, which is part of the VPC. That is true. So we'll take a look at the case, exactly the specific failure cases that is going to happen in. Then can you please describe what are the functions of the primary over the secondary? We're going to talk about that now. Okay, so before we get into the specifics of the failure scenarios, there's another additional design that I want to show here, which is going to be our back-to-back VPCs. So in this case, we're going to be doing a VPC from the 7Ks that are going down to the 5Ks. So we're going downstream with a VPC here, but we're also going upstream with a VPC. So from the 5Ks up to the 7Ks. Now, what is different about this design versus the other ones that we saw before is that normally on the 7Ks, we would have 2 VPCs. We would have VPC 51, and we would have VPC 52, where 52 is going down to 5K2, here and here. VPC 51 would be going down to 5K1 here and here. Then on the 5Ks, if we were normally doing VPC upstream, we would likewise have two separate VPCs. We'll say that this is 71, which is here and here, and then we would have 72, which is here and here. This type of topology is not supported. Because again, remember that the logical result that we're trying to achieve from the physical topology is that we have a physical triangle. So these are the VPC peers. It's a physical triangle that we're trying to turn into a logical point-to-point channel. But in the case of the back-to-back VPC, if we have two VPCs upstream and two VPCs downstream, it looks like two separate logical connections, and basically just this is not a supported topology. It's not going to work for forwarding in the data plane. So what we actually have to do, if we're doing back-to-back, so we're doing VPC up and down, we would say that there are two VPCs total. So we'll say there's VPC 5 that is on these two ports, these two, and these two. Then on the downstream switches, we'll say there's VPC 7, which is here, 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 and here. So based on these number of links, we can see that each of the devices has 4 links. So it's going to be basically multiplexed on all these different possible ways from the ether channel load balancing point of view. But from a logical view like a spanning tree, we're basically just going to see one individual port channel. So it simplifies the forwarding from a logical point of view, but it makes the forwarding more complicated from a physical type of view, and where we're trying to visualize really what's going on in the configuration for this. Okay, so let's go ahead and set this up. And the first thing that I want to do is we're going to start at the 7Ks, and then we're going to do the VPC down towards the 5Ks. So let's go ahead and get on the command line here. And what I've done is basically removed all the changes that we made yesterday, so we can start from scratch and make sure we're not overwriting any other configuration changes that we had made before. So if we look at the show run, I'll say show run pipe no more, which means I don't have to wait for that more output. It's basically just default config here. So I have the VDCs that are configured, but really the key point is that for the interfaces, there's no interface config here. Same should be true on this guy. If we say show run pipe no for no more, okay, there's nothing configured on the Ethernet links here. Okay, first step then I need to do is to make sure I get basic layer 3 reachability between the devices. Okay, in yesterday's example, we did this by configuring the M1 ports in a layer 3 port channel. We're going to show a different minor variation of this where the link is not going to be natively a layer 3 routed interface. We're going to make it a layer 2 access port channel. Then we're going to use a layer 3 SVI in order to do the keep alive between the neighbors. So first on the first 7K, we need to turn the interface VLAN feature on. So feature interface VLAN. And we'll say that this is going to be interface VLAN, we'll say 4094. So the last VLAN, actually we can't use that one. Let's try 4093. Let's see, which ones can we use? Show VLAN brief. Okay, you'll see these VLAN numbers. These are going to be different. The different reserved ones are going to be based on the different platforms. So 5K works a little bit differently than the 7K does here. So let's try 4,000. That's internal. Let's say 3,000. Okay, there we go. Okay, so it's basically an arbitrary number. Any number, as long as it matches between the two, that's really only all that we care about. Okay, so interface VLAN 3,000. The IP address here we'll say 169.254.0.71/24. I could likewise put this in a VRF. If I said VRF context, we'll say this is the keep alive. I could go to the VLAN, say that this is a VRF member of keep alive. This is then going to make sure that this layer 3 link is completely isolated from the rest of the data plane. So no one would be able to send any traffic to VLAN 3000. It's used now exclusively just for the peer keep alive. Okay, so same thing on the other side. Let's say feature interface VLAN. I have VRF context keep alive. On interface VLAN 3000, I have VRF member keep alive. IP address is 169.254.0.72/24. Okay, then I'm going to have my actual links that are connecting to devices. So on this side, these are interfaces E1, 9 to 10, and these are now going to be switch ports. Okay, remember that the M1 ports or the M2 ports on the Catalyst, or excuse me, the Nexus, Nexus 7000, those are going to be in routed mode by default. So I need to put them into layer 2 switch port mode. Okay, I'll then say that these are part of the channel, channel group 3000. If I wanted to use LACP, I would need to turn that on first. So if I were to say mode active, it says I need to say feature LACP first. Okay, so let's go back to the links. Channel group 3000 mode active. Interface port channel 3000 is switch port mode access. Switch port access VLAN 3000. Okay, and then also I need to enable the links, no shutdown. So same thing on the other side. Let's say feature LACP. Interface E11 to 2. These are switch ports. They are in the channel group 3000, mode active. Interface port channel 3000 is a switch port. Switch port access VLAN is 3000. And then the physical links are not shut down. And let's turn our logging on here, terminal monitor. So if we now show IP interface brief for VRF, peer keep alive, right now it says the link is admin down. So I also needed to say no shut. Okay, same thing on the first side. Interface VLAN 3000, no shut. Okay, if we now, and actually create VLAN 3000, show spanning tree VLAN 3000. Okay, we should see that the port channel 3000 now is running this instance, which it is. Okay, this is the root port, means that the other 7K is the root of the spanning tree for VLAN 3000. But really the goal is I want to make sure I can ping 169.254.0.71 from the VRF keep alive, which I can. Okay, so now I basic layer 3 connectivity. We can create the VPC domain and then specify that that's going to be the keep alive destination. So again, in this particular example, we are using back-to-back physical links for the keep alive link, but it technically doesn't have to be. It can be any link that is allowing us to establish layer 3 reachability. So it could be our normal in-band data links, like maybe going upstream towards the core. I could just have an IP address on one of them and then specify that those are the keep alive destinations. It doesn't have to be on the same subnet to allow that. It's just layer 3 reachability. Okay, so next let's create the VPC domain. We'll say VPC domain 7 for the 7Ks. First, actually, feature VPC. So domain 7, my VPC peer keep alive destination is 169.254.0.71. I need to use the VRF keep alive, and I need to change the source to my local address. Show run VPC. Okay, same thing on the other side then. We'll say feature VPC. VPC domain. Match the numbers between the two of them. The peer keep alive destination is now 169.254.0.71. The VRF is keep alive, and the source is my address, 169.254.0.71. So this should be, the destination should be 72 there. Okay, once this is configured, again, next thing we're going to look at is the show VPC. Okay, is the peer alive? This tells me that I have basic layer 3 reachability over the keep alive segment for them now, over the keep alive link. Okay, now I can move to the next step, which is establishing the peer link. So the peer link in this case is going to be on the F1 ports. Okay, it could be an M1 module, but in this case it's F1. On these links, E2, 1 to 2, will say that the channel group is 3001 mode active. On interface port channel 3001, this is the VPC peer link. VPC peer link should be switch port mode trunk and spanning tree port type network. And no shutdown. Okay, same thing on the other side. Interface E2, 9 to 10. Channel group 3001, mode active. Interface port channel 3001 is the VPC peer link. The switch port mode is trunk, and the spanning tree port type is network. And no shut. Okay, if we now look at the show VPC, what we should see is that there is going to be the election for the Cisco Fabric Services, and we should see that there's an adjacency. Okay, it's talking about the CFS adjacency. Peer adjacency formed, okay. If we were to look at the show CFS, or show CFS application, we should see that VPC is using CFS over the physical Ethernet link. Again, this is what we need to exchange our control plane. So we would need to make sure that this is not filtered out. Under normal circumstances, you cannot deny the CFS in the data plane, but we just need to make sure that there is connectivity there between them. Okay, so now we're ready to actually configure the member ports. So the peer link is up. Specifically in this case, the member ports are basically going to be everything. So these two, these two, these two, and these two. We'll say that this is VPC 5, going down to the 5Ks. So specifically, these links are going to be interface E2, 11 to 14. And remember, we want to make sure that these are shut down. We're going to shut all the member links down, configure the VPC, activate them on the primary, let the control plane settle down for a little bit, activate them on the secondary, and then we should see the consistency check is correct over the peer link, and then the VPC is actually going to start to forward traffic. So we shut down the member links. We'll say that this is channel group 5, mode active. On interface port channel 5, this is in VPC 5. Okay, the spanning tree port type is network, and the switch port mode is trunk. Same thing on the other side here now. So interface E2, 3 to 6 should be shut down. Channel group 5, mode active. Interface port channel 5 is VPC 5. Switch port mode is trunk, and the spanning tree port type is network. Okay, so now the 7Ks are prepped. Okay, we need to now go downstream and do the same thing on the 5Ks. So let's look at our full config for this step by step. Let's look at this in just our text editor. So we know that we need feature LACP. We need feature VPC. Okay, we then have our VPC domain. We'll say this is domain 5. The peer keep alive destination is going to be the management link. So we'll say 192.168.0.52. Okay, this is going to be on 5K1. Then we have interface E1, 1 to 3. E1, 1 to 3 here, this is going to be for the peer link. So these are switch ports. They are in the channel group. We'll say channel group 50, mode active. Interface port channel 50 is switch port mode trunk, spanning tree port type network, and the VPC peer link. And no shutdown on the physical ports. Okay, so this is prepping the basic control plane of it. Again, the peer keep alive link and then the peer link. So let's say terminal monitor, we'll turn logging on. And then let's paste this in the first 5K. On the other side, it's going to be the same, just the exception is going to be the peer keep alive destination is different. So that's for 5K2. If we look at the show VPC, we should see that the peer is alive. And then once this converges, the control plane, peer adjacency is okay. Okay, 5K2 is the secondary. This should mean that 5K1, when we show VPC, is the primary. Okay, peer adjacency is up. Okay, so now again we're ready for the actual data plane. So data plane is going to be on E18 to 10 on both sides. So we'll say that this is going to be VPC 7. And for clarity of the config, it's probably a good idea to do some additional documentation in here. Like if we went to these links, E18 to 11, we could say like description, this is for VPC 7, just so, you know, VPC 7 to the 7Ks or something like that. Of course, you don't necessarily have to do that. It's just nice kind of for the management afterwards to make it a little bit clearer exactly which VPC is used for what function. Okay, so we have the member links there. This is going to be, we'll say no shutdown. That's fine because on the other side, they're already disabled. No shutdown. This is going to be channel group 7, mode active. Interface port channel 7 is switch port mode trunk, spanning tree port type network, and VPC 7. Same thing on 5K2. So interface E18 to 11, no shutdown, channel group 7 mode active. On interface port channel 7, this is switch port mode trunk, spanning tree port type, network, and VPC 7. Okay, so now we're at our very last step where the links are disabled upstream on the 7Ks. We're going to go to 7K1, which is the primary, and activate these. We should see that on the 5Ks downstream, a portion of the VPC comes up, not fully. Then once that is settled down, we'll go to the secondary, enable those links, and then we should see it's going to be the back-to-back VPC bidirectionally between them. So on 7K1, let's say on those links, which are, if we show VPC and show port channel summary, these are interfaces E2, 3 to 6. No shutdown. Notice here we have VPC log message, VPC 5 is now up. Okay, these physical links are now members of the channel. Bridge assurance is blocking VLAN 3000 on the port channel, which is probably what we want because VLAN 3000 is only used for our pure keep alive between the 7Ks. So again, when we're running spanning tree port type network, we're using that bidirectional BP2U as a keep alive, but also the result of that is similar to VTP pruning, where it's automatically editing, essentially dynamically, the allowed list of the trunk, saying that they're not sending me VLAN 3000, so I'm not going to send VLAN 3000 to them as well. Okay, we will still send the BP2Us in the control plane, but no traffic is actually sent in the data plane. So if we show spanning tree VLAN 3000, we should see on the port channel that this is now blocked because there's a bridge assurance inconsistency, which is actually what we want to see here. Okay, if we now show VPC, we should see VPC 5 is up. If we go downstream and show VPC, VPC 7 is up. On the 7K or 5K2 as well, VPC 7 is up. Okay, last step, we have the physical links on the other side. If we show port channel summary, these are links E2, 11 to 14. No shutdown. If we show VPC, we should see now our local ports are up. If we look downstream, VPC 7 should still be up, but if we look at the show port channel summary, we should see that all 4 of these links are now they're now members of the VPC or of the port channel. And if we were to look at the show spanning tree, let's say for VLAN 1, for example, the 5K1 is saying I'm the root of the spanning tree. Okay, to clarify this a little bit more, let's go up to the 7Ks and let's actually change the priority. Let's say spanning tree VLAN 1 priority is 4096. Then let's look at what the result of the output of this for show spanning tree is on all 4 of these peers. If we show spanning tree VLAN 1, 7K1 says I'm the root. 7K2 should say that the peer link is the root port. If we look at the 5Ks, they should see from show spanning tree VLAN 1, they see the single VPC is the root port. Okay, the peer link still needs to be forwarding. This needs to be designated because if there's any control plane messages or there's any orphan port data plane or multicast data plane that's actually used in VLAN 1, we will need to forward that over the peer link. But the key here is that now from spanning tree's point of view and from the rest of the data plane's point of view, this entire physical topology is logically collapsed down into this with an 8-way port channel. So 7K at the top, 5K at the bottom. So as you can imagine then, from the rest of the data plane operation, this simplifies the network greatly because we have tons of different possible directions that we can be forwarding. If any of the individual switches goes down, we don't really need to worry about the failure because we should still automatically get sub-second convergence. If any of the individual links goes down, likewise, we basically have 7 left over. So we have essentially 80 gigs of possible throughput between the devices here. Okay, so let's recap our full config here. If we look at the 7Ks, and let's say show run pipe no more. So again, first we have LACP and VPC on globally, the features. We then have the VPC domain and the pure keep alive. So the domain name or the domain number here, it needs to match on the other VPC peer, which is the other 7K in this case. Okay, the actual addresses here, these are the switch virtual interface. It's that layer 3 VLAN interface, but that's kind of arbitrary. It could be the management. If we had separate physical boxes, it could be a point-to-point layer 3 link, could be a point-to-point layer 3 channel, it could be over any other routed infrastructure. As long as I can ping between these 2 addresses, that's all that I really care about. Okay, so that's the particular SVI. Then we have the peer link. Okay, the peer link again has to be a layer 2 trunk, has to be carrying the VLANs that are in the VPC members, and we would want it to be spanning tree port type network. So if we accidentally leave a VLAN on the link that's not being used, then bridge assurance is going to block that and make sure that we don't have additional unnecessary data plane traffic on the peer link. Because again, peer link, we want to keep that mainly just for the control plane. So then we have the final VPC member port. Since this is interconnectivity between the switches, we want to say that this is layer 2 trunk, that's a port type network, and that this is VPC 5. Okay, again, this number has to match between the VPC peers. The port channel number doesn't necessarily have to, but again, you really wouldn't want to mismatch it. The config is clearer here when you match the VPC number to the port channel numbers. Okay, there's a couple questions here. Don't we need the peer switch command for the single switch's ID in spanning tree? Okay, good question. If we look at the 5Ks and we look at the show spanning tree, notice that we see the root bridge is the same value here, okay, between the different devices. Really, the only thing that's different is what's the root port number. The upstream device, 7K1, if we show run include spanning tree, This physically is the root bridge. Okay, so out of those 4 devices, this is the actual root, the spanning tree protocol root. But on the downstream 5Ks, they see these links that are part of the VPC going to the other upstream peer as their normal root ports for spanning tree. So it's actually a modification of the behavior of spanning tree here when we're doing VPCs, that the VPC secondary is not going to be generating its own BPDUs on the VPC member ports. So again, the key is that regardless of where the root bridge placement is, the root bridge could actually be the secondary VPC peer, but it's the primary device that is in charge of basically maintaining the control plane. So from the downstream switch's point of view, they only see one root bridge upstream, where in reality that's not the case. There's 2 switches. One of them is the root, one of them is not the root. But there is an additional feature here. We could say under the VPC domain, we say VPC domain 7, which is the peer switch. On both of the switches, if we say VPC domain 7 peer switch, then I would want to change my spanning tree priority to be equal between the 2 of them. So if we say spanning tree VLAN 1 priority is 4094 or 4096, and we now show spanning tree VLAN 1, 7K2 says I'm the root, and we show spanning tree VLAN 1, and the other 7K says it's the root. So this is basically kind of a hack on the spanning tree process, that there's 2 root bridges, but they're working in conjunction with each other because of this peer link to synchronize the control plane. So it's not the normal behavior of spanning tree. From the downstream switch's perspective, we're now receiving BPDUs in all of the ports, but they're all equal. It's the same priority, and it's the same bridge ID that's coming in. Okay, the reason why you would want to do this, we're going to talk about this a little bit later, has to do with certain failure scenarios where the primary VPC peer goes down, the secondary becomes operational primary, the primary comes back, is re-elected the root bridge, then we have to go through the STP synchronization process in order to reconverge. And in high availability environments, you would not want that because you're going to have a temporary disabling of the data plane. When you go through synchronization, what you have to do in rapid spanning tree is to basically temporarily block all your downstream ports, do the handshake on the root port, agree that yes, you are the root, I'm downstream from you, then you can unblock your designated ports and continue the handshake downstream, which is the synchronization. So it generally is a sub-second process, but there is some measurable time that the convergence takes. And especially in high availability environments and very low latency environments, like if you're doing high frequency trading, you would not want to add that additional latency to the network control plane convergence. Okay, but we will come back to revisit that again as well. Okay, there's a question, is back-to-back VPC a double-sided VPC? That's the same term, right? Yeah, double-sided VPC is the same thing as back-to-back VPC. There's another question, do you think it's a good idea to use the SVIs? I think you have to filter this VLAN from the VPC peer link. Okay, yes, you would want to do that, and I actually did not do that in this example. The SVI that I used on the peer keep alive, I don't want that to run on the peer link. So what I would also need to do is to go to this port channel on both sides of the switches and say that the switch port trunk allowed list is going to remove VLAN 3000. Because I want to use 2 separate physical infrastructures for the peer keep alive versus the peer link. Okay, peer link is for synchronizing the control plane. Peer keep alive is just to make sure that we don't run into that active-active split brain scenario. There's another question. As per Cisco, why do they say for double-sided VPC the number has to be the same for both sides, and I have configured 5 and 7? You could actually use the same VPC domain number. So the way that I configured it here, I said that regardless, there's going to be 2 separate domains. Okay, I said that there was VPC domain 7 here, and I said there was VPC domain 5 down here. Now, what does this number really mean? Where is this information exchanged between the two switches? Okay, they need to have the same number if they are peers with each other, but what link are they using to exchange this information? Okay, they're using the peer link, which is for the synchronization of the control plane. The peer link, there's two separate physical ones in this case. There's a peer link between the 7Ks, and there's a peer link between the 5Ks. What's running over this is the Cisco Fabric Services over Ethernet protocol. So even though I do have layer 2 connectivity between the two separate domains, even if the numbers were the same, it's not going to make a difference because I'm not running CFSOE for the VPC process on those normal VPC ports. It's only on the peer link. So I would say personally, I would keep them as separate numbers just for clarity, that each pair of switches you would just choose a new random number. Okay, it doesn't have to really mean anything, just so when you're looking at the config, if I'm 10 on this side, I should be looking for 10 on the other side. If I just use number 1 over and over and over everywhere in the network, it gets a little bit more confusing when I'm trying to do any type of verification or troubleshooting. There's a question, why would you use double-sided VPC instead of two VPCs facing downstream? What is the benefit? The benefit is that it looks like one logical link from the perspective of the load balancing and from the perspective of spanning tree. So when I'm sending frames north from the 5Ks up to the 7Ks, I basically have 8 possible different decisions. So there's 4 physical local ports on each of the switches. Then based on the ether channel load balancing, I can choose either of those. Okay, same for the southbound from the 7Ks downstream towards the 5Ks. We just have more links to do the load balancing between. Okay, it's basically the same as if I had 2 physical chassis, one upstream, one downstream. I connected them with 8 10 gig links and put them all on a channel. That's the logical result of what we're doing here. Okay, so it looks like just 2 switches from the logical result. There's another question. The pure keep alive, could this also be set up as a layer 3 ether channel instead of an SVI? Yes, it could. Okay, we looked at that example yesterday with the 7Ks using the layer 3 port channel. There's a question, why do you have to change the source for the pure keep alive links? When you're not using the management link, you have to change it. If you just say pure keep alive destination, and let's look at that config difference actually between the 5Ks and the 7Ks. On the 5Ks, if we show run VPC, I said the pure keep alive destination is just this address. Okay, this assumes that you're using management 0 and you're using VRF management. If you're not using that, that's when you have to specifically tell it. If we show run VPC, I'm saying this is the destination, but the destination is not out management 0. I need to send it from this source in this specific routing table, so VRF keep alive. If we show IP route VRF keep alive and compare this to show IP route VRF management, or just show IP route talking about the default global routing table, we can see these are 3 different logical distinctions. So only in the keep alive VRF do I have these 169.254 addresses. And VRF management, these are my management 0 addresses, 192.168.0. And then I don't have anything configured yet in the global routing table here. Okay, there's a question, can we use M ports instead of F ports? Yes, you can. Okay, we'll see for VPC, there's not really restriction for that. The restriction is going to come in when we get into Fabric Path, and then when we configure VPC Plus. So VPC Plus is the combination of VPC and Fabric Path at the same time, and the requirement is that Fabric Path can only run on F1 or F2 ports on the 7K. So it means that your peer link would have to be either F1 or F2. So in our case, they're going to be the F1 ports. There's a comment here, you can change the system reserve VLANs in global config mode. We could change those if we wanted as well. They're just arbitrary numbers. As long as you have like documentation that you know what VLAN is used for which, it's fine. Again, if we look at the show interface trunk like we saw yesterday, we will see, and it's actually different between the 5Ks and the 7Ks, show interface trunk. You could see what's allowed here. There's ones that are removed that are the reserved VLANs. So you could change these if you want to, but in my case I just used a different number that wasn't reserved. Okay, there's a question. I guess this is similar to 2 VSS pairs connecting to each other, No, but instead of 2 control planes, 1 per pair, there are 4 control planes. That's correct. Okay, so with VSS, basically VSS is 2 6500 chassis that are connected with the VSL. VSL is like the peer link in the case of VPC. Okay, the difference is that over the VSL, there's basically an election process that they say one of them is going to be the VSS primary, the other one is the VSS secondary, like the standby. So only one of the supervisors is in charge of controlling both of the physical chassis. So even though there's 2 physical boxes, there's only 1 control plane. So when you do management changes, like you telnet in or you connect the console, you only connect to the active supervisor. Okay, in the case of VPC, we have 2 separate control planes, which again means that if I telnet to one box, I telnet to another, they're just different interfaces. I can make different changes. So even though in this final result, the logical topology, again, looks like this, where we have 1 upstream switch with 8 physical links going to the downstream switch. Okay, so this is the logical, but we know that the physical topology is actually these 4 boxes with the full mesh of interconnectivity here. So there's 1, 2, 3, 4 control planes.